Okay, welcome back to Math 330. We're going to learn how to solve a new type of differential equation, sometimes called the standard form, or using a technique referred to as the integrating factor. This is a first-order differential equation. Alright, so far we have solved what are called separable differential equations, and these separable differential equations have always had the derivative on the left-hand side and some function on the right-hand side that can be made up of a product of two functions. One is just a product of the independent variable, and the other one is a product of a dependent variable of our solution. So if we do that, we have to figure out, we can solve these so far, I hope. And what does this new form look like? They look like this. So you have your derivative plus some function of x called p. Our solution, we're looking for y of x, and then that is equal to some function of q. The problem here is you can never separate the functions of y from the functions y of x from a to p of x's or q of x's. So how do we solve these? We can't use our separation technique. Mathematicians never like to do anything new if they can use ideas that they know from before. And the idea we're going to use is the product rule of differentiation that should help us do this. So if I got a product of two functions and I take their derivative, I get the derivative of the first function times the second plus the derivative of the first function times the derivative of the second. Now, the trick is here is these are both derivatives of functions of x. Although I have this as a product of two separate functions of x, we can kind of ignore that and treat that as one function. So our hope here is if we can come up with the left-hand side of a differential equation that looks like this, that we can rewrite as a derivative of two functions, we might be able to use our separation of variable technique to solve our differential equation. And we're going to do that by using an integrating factor. So what is an integrating factor? Well, it is a function that we multiply times our differential equation. And what we hope this function to do is allows us to simplify the left-hand side of this equation into the derivative of the sum of two functions. So let's do that. So if I carry out the distribution of mu across my differential equation, this. And now I want to go back to the derivative of the product rule right here. And if we look at this, these two are very similar. See, there's our function y, and then here's our derivative of y. Oh, here's mu of x, and here's mu of x. They're both multiplied times the same function. So, seems I have this group of functions left over and this group with a derivative. Now, if I want this to be true, this and this need to be equal. So this is the condition I'm going to choose. I create this new condition, and from this I hope to be able to find mu. Well, we should be able to find it because this is now a separable differential equation. And we should all know how to solve this by now. So if I separate it, put all the mu's on the left-hand side, put everything else on the right-hand side, I get this. Integrate both sides, I get the log of mu is equal to the integral of p dx. Now I want to get rid of the logarithms to find mu. So here is my integrating factor. All I have to do is integrate this function p of x dx and then take it, put it in the exponential function as the exponent, and I have an integrating factor. So here's what we had before. Now I can convert it to look like this, and so this is our differential equation. Well, this is just a function of x now. There's two functions of x. I know what this is. I know what this is. This is a separable differential equation. So we can solve this. Or I hope everybody can solve this. So if I separate it, I have just a differential here. If I integrate both sides, what happens? Well, this just gives me my function mu back and my solution I'm looking for, and an integral I should be able to solve plus a constant. So if I divide by mu, I have the solution for our original differential equation. And we get this by using techniques that we already know and a trick called the integrating factor. So let's do an example. Let's say we have this differential equation right here. Now this is represented in the form I know, and if it's not, you have to arrange it this way. So we could use some of our old techniques that were of a direction field for this, so to solve this differential equation. And it appears as x gets large, everything converges down to the value of 2, which is probably about right. That's what it needs to be. But how do we find the exact function of y? Well, we know that p is 1 because p of x has to be multiplied times this value. Q is 2. Since we know p of x, I can find the integrating factor. And so I integrate this, I get just e to the x. Alright, so we multiply by our integrating factor, and we get this expression, and we carry out the exponential. And if we look at this, here's the derivative of y with respect to x. Here's the function of y. Here's the first function, e to the x. Well, what's the derivative of e to the x? Well, it's just e to the x. So this is a derivative too. So this is a product, a derivative of the product of two functions. So I'm going to write it that way. And now it becomes a separable differential equation. And if I move the x over here and I integrate this, I get my two functions back. And the integral of 2e to the x times integration constant c. And if I divide by my e to the x to just get y, I get this solution. Now you can see as x gets large, this is going to go to 0 and our solutions are going to go to 2. So this is how you solve first order differential equation that comes in the standard form with the using the integrating factor. So I'll do another example to practice. This one we're going to give you an initial condition. So here's our differential equation. So again, I plotted this with the direction field to see what happens to my solution here. And I only have one solution here because I have initial condition, and it goes through 0. So in this case, p is minus 2, q is 3 times e to the 2x, and then this should be where I find my integrating factor. And so if I integrate this, I get minus 2x, e to the minus 2x. So now I'm going to multiply that through my differential equation, and I get this. And if we look at this again, here's the derivative of y. Here's y. Here's e to the minus 2x, and here's the derivative of e to the minus 2x. So I can write this as a derivative of two functions, e to the minus 2x and y of x. And it's just equal to 3. And so now I can integrate both sides, and this integral is just going to give me my two functions back, and this integral is just going to give me 3x plus some constant, and I divide by my new exponential, and I get this expression. Okay, well now I got to find d by applying my initial condition. Well, when t is 0, or when x is 0, I put zeros in where the x's are, y has to equal 0. So this is 0, and I get d times 1. Well, d has to equal 0. So this is just going to make our solution this. Now, if you wanted to check to see if I'm right, you can take the solution and plug it back into the differential equation. Or if you want to practice your maple, you can take the derivative of this and then add it like the differential equation and see if the left-hand side equals the right-hand side. Alright. A way these standard form differential equations show up in applications-wise is what's called a mixture problem. So you have this tank of a certain volume, B of t as you call it, and the idea is to try to predict the amount of dissolved solids in the liquid. How are we going to do that? Well, we're going to look at how much mass of the dissolved solids is changing over time. And the way we're going to do that is we have a certain amount of liquid coming in, a rate of liquid flow coming in at a set concentration, going into a volume here, and then there's also an outflow, a set outflow, where there's a flow rate going out and a concentration that's flowing out. Now, to do these problems, we assume this liquid here is all well mixed. Everything's in equilibrium. Everything is evenly distributed across the volume of the liquid. Okay. So how do we do these? Well, we'll claim X is the amount of the dissolved substance in the liquid that we're looking for, and we're trying to see how fast that changes in time. So we have to know how fast it comes in, the input, that's here, and we have to know how fast it's going out, that's here. So inputs are positive, outputs are negative. So now we have to figure out a way to figure out the amount of material coming in per unit time and the amount of material going out per unit time. So the way we do that is this is the input and then this is the output. So the way we do that is we look at an expression like here where Ri is the rate of flow in, Ci is the concentration of the material in, the rate of flow out, and the concentration of the flow going out. Well, how do you figure these out? Well, we have to know a little bit about flow rate and how to calculate a concentration of an element in there. The way we do this is this. We want this to be, say, grams per time. So a flow rate is the amount of volume or liters coming in per unit time. A concentration is the amount of material, or grams of material, per unit volume, or liters in this case. So if you can't, these liters cancel and you get grams per second, and that's exactly what we want here, is grams per second. Well, how do you figure out flow rates? Or I should say, how do you figure out concentration? Well, by definition, the concentration is the amount of grams per volume that it has. What's the flow rate? Well, the flow rate is a volume per unit time. So when these two multiply, the volumes cancel, just like we had here, liters are a volume, and you get an amount per second out. So here, let's do one of these problems, because these are word problems. And now, here's the word problem. We have an initial tank containing 60 gallons of pure water, a brine containing 1 pound of salt per gallon enters the tank at 2 gallons per minute, and then a perfectly mixed solution leaves the tank at 3 gallons per minute. Thus, the tank empties in 1 hour. They want to know the amount of salt in the tank after some time t, and what is the maximum amount of salt ever in the tank. Alright, how do we find this information? Well, I'll set you up so that you can find it, and I'll let you find it for yourself. So how do we do this? Well, we got to set up a differential equation. So this is the derivative. So this is X is the amount of salt per unit time. So we're taking, that's the rate in the tank per unit time. Alright, so this is what's coming in. So what's coming in? We have 1 gallon or 1 pound of salt per gallon. So this is a mass per volume. That's 1. And the concentration is gallons. Okay, sorry. The rate is a volume per time. So volume here divided by time. So you get the volume on the bottom of this one, cancel this one. So you get 2 out here. And you can subtract out what's going out. So this is a tricky one. So how do you do this one? Well, the flow rate out is 3 gallons per minute. Okay, that's this 3 right here. Well, how do you get the concentration? The rest is the concentration. How do you get that? Well, X is the amount of salt in the tank at any time t. And it's all well mixed with the volume in the water. Well, now we have to figure out how much volume is in the tank. Well, that's this. This is volume. Initially, it's 60 gallons. And I add to it whatever comes in minus whatever goes out. So it's coming in at 2 gallons per minute. It's going out at 3 gallons per minute. And then if I multiply that by time, this is a volume unit. So I have a volume here plus another volume. This gives me the volume of liquid in the tank. And if I divide that into the amount of salt in the tank, I get the concentration. So we need to solve this. This turns into this if I simplify it. And then if I rearrange it to look like one of the standard form equations that we're talking about, it looks like this. So let's see if we can solve this, or at least find out what x is over time. Here we go. So P of x is this. Q of x is just 2. We need to find our integrating factor. Here it is. I need to integrate this. This is you have to integrate this by using u substitution, where this is the u. And when I do that, I get this solution. Now, how do you get rid of this logarithm? Well, you have to use some properties of logarithms. So anything multiplied times a log can be rewritten as the log to that exponential. Well, now I'm taking, sorry, not exponential, exponent. I'm taking the exponential function to a logarithm, and I get this. So this is my integrating factor. So I multiply that through my differential equation. I have this. Now if you look at this, here's my derivative of x. Here's x. This is my function. 1 over this. If I take the derivative of that, I get this. So I could rewrite this. How do I rewrite it? Well, I rewrite it as a product of these functions and set it equal to my q of x. Now I have to integrate both sides. If I do that, I get this function back, because this is just a total differential. And if I integrate this, I get this plus some constant d. Now I need to find x, so I multiply by this expression on both sides, and I get this. Now I have to find d. Well, what's the initial condition? How much salt is in the tank at t equals 0? Well, if you go back and read the question, it says initially the tank has 60 gallons of pure water. So that means we have 0 salt in the tank at t equals 0. So if we plug that in, we get this. We can solve this for d. There's my integration constant right there. Now if I plug that back into x, I have my derivative, or I have the solution to this differential equation. I know how much salt is in this tank for any time t. Now, part B says, what is the maximum amount of salt in the tank? So you guys have all had calculus. I have my x of t. How do you find a maximum of a function? Let's see if you can answer that on Tuesday. All right.